Welcome to the course on advanced power electronics. We will have a topic 6 today on the non-isolated DC-DC converters. These non-isolated DC-DC converters are classified into major three categories like buck configuration, buck converter configuration. So starting with the simple buck, then we have a half bridge buck and full bridge buck, and many more configurations are reported in the literature. Similarly, boost configuration also like a first basic boost, then half bridge boost and full bridge boost, and many more. Apart from that, we have a buck boost converter in which buck and boost operation is in the same converter. So starting with the simple buck boost converter, then we have a cup converter, then SEPIC single-ended primary inductance converter, then Zeta converter, Leo converter, and canonical switch converter, and many more in this category also. Well, where are the application of this non-isolated DC-DC converter? Typically in battery charger, electronic ballast, for lighting system, measurement and testing equipment, small rating motor drive in medical equipment, small rating refrigeration unit, and single stage with power factor correction, and many more. So starting with first, you can see the photograph of fuel cell DC-DC converter. How it look like, which use typically non-isolated DC-DC converter. Then battery chargers, as you can see, for charging the battery, we use the DC-DC converter for controlling the charging current. Then battery charger for laptops. Then electronic ballast for typically for earlier in CFL and nowadays in LED lighting system. You can see DC converter has a dual digital control LED lighting system. Then touch screen monitor LMB DC converter is controlled by DC. Then using a DC converter for to power the lasers. Then in medical equipment, the DC converter are very extensively used for most of the electric parts which are operated normally by DC supply, and many more. Now coming to the first category of buck category of the DC-DC converter. So this is the circuit of simple buck converter where we have an input DC source, then we have a switch. Depending on the power level, different kind of switches are, but MOSFET are preferred normally for low power. Then we have a diode, inductor and capacitor, and output we have the load. And for continuous inductor current and ideal condition, the output voltage is a function of duty cycle D into Vn. And if you look into on the right side, first we keep the switch on. There are typically in continuous conduction mode, there are two modes. One when the device conduct. So first one is when device switch conduct, as you can see in the circuit. The diode become reverse bias and switch conduct and inductor current increases, and this results in positive inductor voltage VL equal to VD minus VO, as you can see in the waveform also, and it causes the linear increase in the inductor current like equal to this, you can call it VL equal to L di by dt. So you can say in this case, your IL becomes 1 upon L integration of VL into dt. Now coming to buck half bridge converter, as you can see the circuit, here the output voltage becomes 1 by 2 in bracket 2 D1 minus 1 Vin, because you can operate either upper switch or lower switch, so it becomes 2D type. And we have output again inductor LC filter across the so that output voltage is ripple free, so that load does not, and LC filter really filter out the switching ripples in this converter. And of course this value of this LNC reduces as you increase the switching frequency, that we'll look into later. Then we have a full bridge DC-DC buck converter. So here the output voltage is equal to 2D minus 1 into Vin, and it can of course have a bidirectional polarity also, but normally in such a DC-DC converter we need only unidirectional polarity. Then coming to the boost converters, as you can see here, we have a VD as a source, then inductor, then switch, diode and capacitor, and then output voltage is function of V input or VD upon 1 minus T. So boost converter has output voltage larger than the input voltage. It can also be operated in both mode, continuous inductor current mode and discontinuous inductor current mode based on the inductor current. This boost converter is very extensively used in number of applications as well as other converters such as power factor correction converters. Now coming to boost half bridge DC-DC converter. So you put like a coupled inductor in between the two devices, and so it really, because of this inductor, we have the buck operation converted into boost operation, and the transfer function becomes VO equal to Vin divided by 2 in bracket 2D minus 1. Similarly, the boost converter, here full boost full bridge converter. You put the inductor at the input, it becomes a current source with the supply, and then we have a bridge similar to like earlier and with the output filter capacitor. So then it becomes VO equal to V in divided by 2D minus 1. Then we have another third category of the DC-DC converter called buck boost DC-DC converter, where we have of course the only the location change. After the supply we have a device switch, or you can call it MOSFET, and then with the followed with the inductor, diodes and capacitor, and output voltage is dVd upon 1 minus d. So boost here, the buck boost operations, buck boost converter is very widely used converter because it is capable of bucking and boosting the input voltage to obtain regulated DC output voltage. So you can really control the voltage over a wide range, starting from typically 0 to even higher than the input voltage. Then Cuck converter, it was invented by Cuck, Pavan Cuck, and in this case also, of course, we use the two inductors. We have a supply voltage followed by inductor, then device, then the capacitor, diode, and inductor, and the output capacitor across the load. So output voltage becomes VO equal to dVd upon 1 minus d. And important, this converter was, when it was invented, it was considered that the inductor current ripple will be, you will not have any ripple current in the source as well as in the output load because of L1 and L2. So it becomes noise free converter, and it means you will not have a too high ripple at the output also, similar to buck converter, and you will not have a typically even the input, because of input inductor, you will not have a similar to boost converter ripple in the input also. And of course capacitor is also this. So of course we use here the additional component in the sense that one additional inductor compared to other classical converter like buck converter and boost converter, but it gives a great advantage that you have a ripple free input current and ripple free output current with the noiseless operation, and the energy transferred through the capacitor. Of course there is one drawback similar to buck boost converter, that the output voltage polarity is reversed in this case also. Then on the same basis we have a SEPIC single-ended primary inductance DC-DC converter, where the number of components are same, except here the output inductor plays with the diode change location, and output transfer function is d upon 1d minus 1d. But the advantage of this, the output polarity is not changed. So you have to certainly have some disadvantage. Like now the diode will keep the same kind of polarity of the output voltage as the input, but of course input current ripple is reduced. Here of course source does not have any ripple current, but of course output you have a filter capacitor, which also give ideally with the large capacitor you give almost constant voltage across the load. Then we have a Zeta converter. Here of course again the location of input inductor and typically the device is changed, and you have again energy transfer capacitor followed by the diode and inductor and the capacitor. So here also the output polarity does not change, but of course the disadvantage is that input current is discontinuous because device is connected in series, and transfer function of this also V equal to d into Vd upon 1 minus d, where d is the duty cycle of the switch. And now there is another converter called Leo DC-DC converter. In Leo DC-DC converter, of course we have an input filter L and F, then the switch, inductor, diodes, and typically the capacitor, followed by output filter and HC. Of course here also polarity change, and VO equal to dVd upon 1 minus d. So this also buck boost converter. It was invented by the Lu, that's why the name there, but of course we have a additional inductor capacitor in comparison to the other typically the 3 buck boost converter. Then we have a canonical switching DC-DC converter. Here also you can see VO equal to dVd upon 1 minus d. Of course here also the polarity of output voltage reverse, but here you can just see the only inductor is 1, as well as there is only one capacitor, so we save the one inductor in this case. So when switch conduct, it stores the energy in that inductor, and when switch typically or switch off, inductor current direction cannot change, so diode really charges the output capacitor typically for feeding the power output or energy transfer. So this is called canonical switching cell converter. Is a buck boost converter and uses one solid state switch. It has 2 capacitor and 1 inductor and 1 diode. So coming to now typically a linear power supply, which was earlier used for DC-DC conversion. So it was having a very poor efficiency. Why this switch mode converters appear, and it was having large size of the weight. The reason being, you can see after the we reduce the voltage with your power frequency transfer of 60 Hz or 50 Hz, depends on input supply, 3-phase or single phase. We use the diode rectifier, and it gives the Vd and this VD presumes that it will be always higher than the output voltage, even the input voltage vary. So you can see the range of the VD. So it is to make sure that the output, the VD remains always higher than output, and then we have a series, you can call it a BJT transistor, which work as amplifier, and then output voltage we regulate with the error amplifier or controller to control the base current. So here the transistor operates in amplification so that it provides your variable resistance so that output voltage is ripple-less. Here it is not having any ripple because transistor is operating. So advantage is that you don't have a ripple in the output, but a major disadvantage is of this circuit is that your efficiency is very poor because there is a large losses. If you look at linear power supply, even for very low power of around 60 watt, you'll find the weight of typically around 4 to 5 kg because of power frequency transformer, as well as a large heat sink required for the BJT to cool down the BJT, and several BJT sometimes to increase the power rating are connected in that. To replace this linear power supply, when we use switch mode power supply, where we use this switch mode power converter, DC-DC converter like. So of course here we can call it, we use the pulse width. DC-DC converter, we use the pulse width modulator converter for remaining DC-DC converter, and you have a controller, we call it amplifier, and the control voltage compare with the repetitive waveform as you can see in the waveform, and give the switching signal for the switching devices in most of switch mode DC-DC converters like. So now coming to DC-DC buck converter for analysis. So buck converter is used for driving the DC voltage source, and LC low pass filter is used at the output, and the diode provides the freewheeling converter path for the inductor current when solid state switch is offers, and it remains reverse bias when switch is closed. The converter is known as buck converter because the output DC voltage is always less than the input DC voltage. There are two modes of operation depending on the inductor current. If this inductor current remains a positive, then it's called continuous conduction mode, and if this inductor current becomes 0 for some period, especially during the period of solid state switch, then it is known as discontinuous current mode. So you can just see the circuit of this your buck converter. Here we have a source, then that switch, followed by the inductor, capacitor and diode and load, and the output. For continuous conduction, we have a VO equal to D into V in. This is an ideal converter where we neglect the parasitic effect as well as we consider the both diode and device ideal, as well as we neglect the resistance of the inductor as well as the ESR of the equivalent series resistance of capacitor also. Then this relation is valid. Now coming to the typically here to effectively reduce the DC, so DC equivalent of this DC-DC buck converter is similar to an AC transformer, where we consider it as a lossless objective as a ideal. So where P in equal to P out, which means that V in I in equal to V out and I out, and which becomes V out upon V in equal to I in upon I out, similar to the kind of transformer. So now coming to an example of insufficient DC. So if we have a V in with the R1 and then output load is R2, if we connect simple resistance, so what the kind of efficiency? We output get V in divided by R1 plus R2, that is the current, into multiply R2 output load resistance. So efficiency becomes R2 upon, because that is corresponding to output power, divided by R1 plus R2 and equal to V upon V in. So if we have a V in equal to 39 and V out is 13, efficiency remains only 33%. So that is unacceptable. Because of low power, or use only low power application, because it has a very poor efficiency. That's why we go for switch mode power converter. So now coming to this buck converter, here we have a supply with the switch, then diode, inductor and capacitor, and the different notation are given. So we consider here that the large capacitor at the output, so that the V output has a very low ripple, and since V out has a very low ripple, then assume I out has very low ripple. So inductor voltage and capacitor current average value is 0. So typically, in ideal condition, so here we can say the average output current in the capacitor should go 0, and output voltage across the inductor is 0. If we neglect of course the inductor resistance and capacitor in equivalent ESR, like equivalent series resistance like. So now we can say input output equation of DC-DC converter usually comes by examining the inductor voltage. So the inductor voltage you can say in two mode. It comes when switch is on, diode is reverse bias, so you have an inductor current. Voltage across the inductor is V in minus V out. And of course the capacitor current is IL minus I out, along with the other relations like. So now in that case we can say VL equal to LdIL upon dt, or VL equal to V in upon minus V out, and for d into t second, where d is the duty cycle and t is the period corresponding to one long period, so V in minus V out L di dt, and dIL upon dt equal to V in minus V out upon L. So note that if switch stage closed, then V out equal to V in. So now switch open for 1 minus d period, that's a off period, you can call it off switch, and diode conducts automatically because inductor current suddenly cannot be changed. So then this is the equivalent circuit. The output inductor voltage is equal to minus output voltage across it, and the of course capacitor current is still remain IL minus I out. So IL continues to flow, then the diode is closed, and this is the assumption of continuous conduction in the inductor, which normal operating condition. So VL equal to L dIL upon dt, and or VL equal to minus V out, so or minus V out equal to L di by dt. So certainly you can say dIL upon dt equal to minus V out upon VL. It means the current start decreasing because it's with the minus sign. It remains 1 minus t into d, 1 minus d into t seconds for where the diode conduct, and we consider of course here the continuous conduction mode. So now coming to the average voltage across the inductor, so which is supposed to be equal to VL average d into V in minus V out, that is on period, and during off period when diode conducts 1 minus d into minus V out equal to 0. So from this we get d V in equal to d into V out plus V out minus d, and from which we get input V out equal to d V in. So from power balance, V in I in equal to V out output, so it becomes I output upon I in upon d. Not even though I in is not constant and I in has a harmonics, then the input power is still simple V in I in, because V in has no harmonic. Now coming to buck typically now the second mode, when diode conduct and switch is off. So because of inductive storage IL continue to flow as in shown the diagrams, and you can see in the waveform also how when diode is typically forward bias and the inductor current start reducing because the output negative voltage across the inductor. So now current flow through the diode and VL equal to minus V out, and waveform clearly says the current increases during on period, switch on period, and current decreases in the inductor during off period, and it shows the inductor voltage also. So during on period it is input voltage minus the output voltage, and during the typically your output during the off period is minus output voltage. So now coming to the analysis in continuous conduction mode. In continuous conduction mode, the average voltage across the diode is V d average equal to 1 upon t, 0 to t, where t is the period of one long period, and Vd dt as a dt equal to 1 upon t integration V in into dt equal to V in into d. So if lossless low pass LC filter is ideal, the average voltage across the inductor is 0, and the output average voltage is same as the input average voltage. So Vd equal to Vd average or equal to Vd in, and d equal to T on upon T on plus T off, or T on upon T, or equal to F into T on. So where the d is the duty ratio and T on is the solid state switch on period, and T off is off period, and T is the total period of the switching frequency. So another way of analyzing the operation of buck converter through inductor and capacitor voltage and current, which is used for designing the filter, considering all the components ideal, and in a periodic inductor current is given as IL as a function T plus capital T equal to IL into T, IL as a function of T, the average inductor voltage is 0 as VL equal to 1 upon T, VL as a function of T1 into dt1 equal to 0, and then the average capacitor current is also 0, so IC equal to 1 upon T IC is a function of T1 into dt1 equal to 0. So power supplied by the DC source is equal to the power delivered to the load. So P in equal to P out equal to V in I in equal to VO IO, or I in equal to VO IO upon V in. So for non-ideal components, the DC source always supply losses for the instantaneous quantity when the switch is on or diode is off, and the voltage balance across the inductor is VL equal to V in upon minus V in equal to L di by dt, or dIL upon dt equal to V in minus V upon L. That gives the constant slope of the inductor flow is rising, like in that case if inductor is not saturated. So now since the rate change of inductor current is constant, it rises linearly. It may be modified as dIL upon dt equal to delta IL upon delta t, or delta IL upon capital delta T, or V in minus V out upon L, or delta IL on equal to V in minus V upon L into dt. So for the CCM condition, when the switch is off, then the diode conduction resulting in the voltage across the inductor is VL equal to VO equal to L di upon dt, or dL upon dt equal to VL minus VL upon L. So the rate change of the current is negative constant, and it is decreasing linearly. The change in the inductor curve when switch is off is equal to delta IL upon T equal to in bracket delta IL upon 1 minus D into upon T, and that is minus V upon L, or delta IL of equal to minus VL upon L into 1 minus D into T. So under steady state condition, net change inductor current over a one period is 0. It means delta IL on plus delta IL off equal to 0, and substituting the value of delta IN for both these modes, it becomes VL minus V in upon L into delta T dt minus V upon L into 1 minus D into T equal to 0. Solving this, it becomes V equal to D Vin. As the D duty cycle varies from 0 to 1, thus the buck converter produces output voltage less than or equal to net voltage. An alternate method for deriving the output voltage on the basis of that average voltage of inductor is 0. So VL equal to V in minus VO minus Vt plus V minus VO into 1 minus D into Vt, and from which we get the less than VO equal to D Vin. Now coming to the average inductor current is the same as the average load current, and hence the average capacitor current is 0 under the steady state condition. So IL equal to IO equal to V upon R, and as the ripple in the inductor is known from then the maximum and minimum value of inductor current are as I max equal to IL plus delta IL upon by 2, or equal to V upon R plus VO 1 minus dt upon 2 by 2, or VO or equal to VO in bracket 1 upon R plus 1 minus D upon 2 LF, and I minimum equal to IL minus delta IL by 2, or equal to VO upon R minus VO 1 minus dt upon L upon by 2, and or equal to VO in bracket 1 upon R minus 1 minus D divided by 2 LF. To calculate the filter inductor value for boundary condition between CCM and DCM, I minimum is to be 0. So I minimum equal to 0, and you have VO equal to 1 upon R minus 1 upon minus D divided to LF, or equal to LF equal to LF minimum equal to 1 minus D R by 2, or for desired frequency F, the value of inductor for boundary condition is L minimum equal to 1 minus D into R upon 2F, where L minimum is the minimum inductance required for continuous inductor current. Now coming to typically output voltage ripple in continuous conduction mode. So far the output filter capacitor is considered very large to regulate the output voltage ripple free, and in practical situation the output voltage cannot be ripple free due to the definite value of the capacitor. So ripple in the output voltage may be calculated from the ripple current IC in the capacitor as IC equal to IL minus IR. So when capacitor current is positive, the capacitor is charging from basic relation of charge and ripple voltage, and can be calculated as Q equal to CV, or equal to delta Q equal to C delta V, or delta V0 equal to delta Q upon C. So now coming to typically output voltage ripple in CCM. As you can see the circuit here with the inductor capacitor and output, and the waveform of inductor current. Current rises for during the on period, and off period it reduces, and you get the ripple like an average current of the inductor equal to output current, that is equal to V upon R. And you can clearly see IC equal to, you can see the capacitor current average of which is equal to 0, below is the IC current, the IC equal to IL plus IR. So the change in the delta charge delta Q is due to ripple area in the inductor current above the time axis shaded area. So delta Q equal to half T by 2 and delta IL by 2, that is equal to T into delta IL by 8, which results in delta V equal to T delta IL upon 8C, and or your substituting value IL. So delta V equal to T V0 1 minus D upon T divided by 8 LC, or VO or equal to VO 1 minus D upon 8 LC F square, or in per unit ripple in the output voltage is VO upon delta V upon VO equal to 1 minus D divided by 8 LF square. So the value of capacitor can be calculated for given output ripple voltage. So C equal to 1 minus D upon V0 divided by 8 LF square into delta V0. Similarly, the current ripple can be calculated delta IL equal to I max of minus I minimum equal to V upon 1 minus D divided by DLF. So of course you can say both value, and the inductance value for this for given ripple current L equal to V of 1 minus D upon delta IL into DF. So of course this inductor as well as capacitor both depends on the frequency. So inductor is inversely proportional to frequency and capacitor is inversely proportional to frequency square. So you can clearly see how really the filter value reduces if you increase the switching frequency like how. So this is the design equation from which you can find out the capacitor and inductor for this buck converter in continuous conduction mode. So now coming to non-ideal condition of buck converter. So in the previous analysis, all the components are considered ideal. However, if the operation is at quite low voltage, then the drop across the devices and filter components cannot be neglected. Hence, the effect of device and diode drops are considered as VL on equal to Vn minus Vo minus Vt. That is the let's say device drop equal to I all on into RL. That is the typically the resistance of the inductor. Where Vt is the voltage across the solid state switch, RL is the resistance of inductor. So voltage across the inductor during off period is VL of equal to IL of RL, that is minus VO minus VD. So these are typically, you can say, the simulated waveform of typically buck converter in continuous conduction mode, starting with V input voltage, input current, output voltage, typically output current, and then inductor voltage, inductor current for continuous conduction, switch, typically switch voltage, switch current, diode voltage and diode current. And coming to this under non-ideal condition, the average voltage across the inductor is VL equal to IL into RL, and that is IO into RL, or equal to Vn minus VO minus Vt into D plus minus VO minus Vd into 1 minus D. So solving V0 will be now in bracket V into D minus Vt into D minus VO upon 1 minus D divided by 1 plus RL upon R. So now you can see the output voltage does not depend only the duty cycle and input voltage, but it also depends on diode, typically your diode drop as well as transistor drop, switch drop as well as the inductor resistance, like which certainly deviate from the ideal condition. So where L is the resistance from the inductor and R equal to V equal to load resistance, the value is lower than V equal to Vd in for which is for ideal condition. So it means in practical condition, the output voltage will be lower than the ideal condition. So now similarly, the output voltage ripple is based on an ideal capacitor. A real capacitor may be modeled as a capacitance along with the equivalent series resistance called ESR, and the ESR may have significant value and it may increase the output voltage ripple. So voltage across the ESR is equal to delta ESR equal to delta IC into RC. For estimating a worst condition, the back-to-back ripple voltage due to the ESR may be added to the voltage ripple due to capacitor. However, the peaks of both do not coincide, fortunately. So then you can call it your VOC will be delta VOC will be in between delta VO plus delta VO ESR. So certainly your ripple increases, typically more. So now coming to typically the buck converter operation analysis in discontinuous conduction mode. So you can understand here in discontinuous conduction we have a switch on which is start from zero current, because earlier have been zero, then diode conduct, and at the end of diode conduction certainly current goes below before the device switch on. So there is of course the different period for turn on. Now the diode conduction period is not the typically 1 minus D into T, it is D1 T, which is D1 is lesser than 1 minus T. So you can call it Vn minus Vo into dt equal to Vo d T1 D1 into T equal to 0, or V upon Vn equal to D upon D plus D1. Where D1 is always less than 1 minus D. So you can understand this value increases more than your typically in continuous conduction mode. So where D1 T is the period when diode is conducting and it is less than the T off period of the solid state switch. Now it is required to find out the value of D1 in terms of circuit parameter, which is described in the following section. So coming to average inductor current, IL equal to IU equal to V upon R, and average inductor current as IL equal to 1 upon T in bracket I max dt upon by 2 plus I max T1 T by 2, and that is equal to I max in bracket D plus D1 by 2, and from which we can find out I max in bracket D plus D1 by 2 equal to V upon R. Of course, here the I minimum is 0 because it's a discontinuous conduction mode. And you can see the waveform how really it goes to even for boundary condition, but discontinuous condition is even much you can call it lower inductor, and certainly current become much before than that. So average voltage across the inductor during on period is VL equal to Vn minus Vo, and in solving it, dL upon dt equal to Vn minus Vo divided by L, or delta IL into dt divided dt. It's a delta IL upon dt equal to I max upon dt. So I max from these comes I max equal to delta IL, and that is Vn minus Vo by L into dt, or Vo d1 t upon L from the same triangle. So from this we get I max in bracket d plus d1 by 2 equal to Vo d1 t in bracket d1 plus d1 divided by 2L, or equal to V upon R. And from, of course, this becomes a quadratic equation for d1. d1 is square plus d1 d into d1 plus minus 2L upon RT equal to 0. So solving this equation, we get typically d1 equal to in bracket minus d plus minus under d square plus in bracket 8L upon RT by 2. So solving this, we get the VO equal to V in upon d plus d1, or V in divided by 2d, V in into 2d divided by in bracket d plus under root d square plus 8L upon RT. So you can consider here the output voltage does not depend only duty cycle and the input voltage, but it also depends on component value, typically the load resistance, switching frequency, as well as the inductor value. And of course, you can say d plus d1 is lesser than 1, so therefore the output voltage will be higher in case of DCM than the CCM of buck converter. So now you can consider an example based on upon the waveform, that is often in DC converter current. Decompose the waveform now into ripple plus the minimum. You can say how the in practical you can call I average equal to I max upon I minimum by 2, and how I minimum I average really changes, and you can say the delta IL will be I max minus I minimum. If you take that I minimum, you can out, so you can say the how ripple current is there. Like, so now you can see the waveform typically for even for discontinuous conduction mode of buck DC-DC converter with the input voltage and the input current. Of course, you here the discontinuous because the device in series, then output voltage as well as output current also, inductor current also becomes typically in the discontinuous mode, like, and we saw switch voltage switch current out and out voltage out current. And now you can find out the RMS value of periodic waveform. So I RMS equal to average in bracket delta IT plus I minimum square, and I RMS square equal to average of bracket delta I square plus 2 delta I into I minimum plus I minimum square, or I RMS square average delta I square plus 2 I minimum into average of delta IT plus I minimum square, or I RMS square I max minus I minimum by 3 square plus 2 I minimum, I max I minimum by 2 plus I minimum square. So defining IPP equal to I max minus I minimum, so I RMS square will be IPP square by 3 plus I minimum IPP plus I minimum square. So recognize that I minimum equal to I average minus IPP by 2. So I RMS square equal to IPP square in bracket I average minus IPP by 2 IP into IPP plus I average minus IPP by 2 square. So I RMS equal to IPP square by 3 into plus I average IPP minus IPP square by 2 plus I average square minus I average IPP plus IPP square by 4. And IRMS will be IPP square by 3 minus IPP by 4 plus I square, and which gives you I average square equal to IRMS square equal to I average square, or I plus IPP square by 12. And you can see how it is or in waveform like a IPP difference between minimum maximum and I average, your I max plus I minimum by 2. So I RMS square to I average square plus 1 by 12 IPP square equal to I out square plus 1 by 12 I delta I square. So maximum impact of delta I on the RMS current occurs at the boundary of continuous discontinuous conduction, where I delta I equal to 2 I out, as you can see in the waveform, and I RMS equal to I square 1 upon 12 2 delta I square equal to 4 by 3 I out square, or I RMS equal to 2 by root 3 into I out. And now coming to capacitor current and capacitor rating. We have a capacitor current IL minus I out, the ripple current, and you can say average, of course, this current is 0, as you can see in the typically waveform. The maximum RMS current at the boundary condition of continuous current delta I equal to 2 I out. So I see RMS square equal to I average square plus 1 by 12 2 I out square, or equal to 0 square plus 1 by 3 I out square, or I see RMS equal to I upon I output upon root 3. and you can clearly see MOSFET and diode current how it's there. So the MOSFET current start from 0, so it goes from 0 to 2 out, and the diode current goes again from 2 out to 0 in typically in yellow, blue and green color. And the worst case D for each I RMS equal to 2 upon Y root 3 I out. So worst case load ripple voltage you can typically see from this your ripple current. I mean how it is the charge balancing is there across the capacitor with these current. So delta V will be delta Q upon C or equal to half T by 2 I out by C or T into I out by 4C or I out by 4CF. So during the charging period the C voltage move from minimum to maximum. The area of the triangle shown above give the peak to peak ripple voltage, and raising F or L reduces the load voltage ripple. I mean typically. So now coming to voltage ratings. Now if switch is closed, you can see the circuit how it is the current flowing inductor and capacitor, and diode is only V in, and when MOSFET is off, so diode conducts and switch is open, and you can see the current in the inductor capacitor voltage. Diode and MOSFET use 2 V in and capacitor use 1.0 V out. You can find out the onset of discontinuous current in boundary condition. You can see how the current average current typically goes inductor current your 0 to 2 I out, that is minus V out upon L. So you can find out 2 I out equal to V out upon I onset into 1 minus T to T equal to V out 1 minus T L onset into F, or L onset equal to V out upon 1 minus D upon 2 out into F. That is a boundary condition of the inductor. Then considering the worst case, D goes to 0, so L will be much larger than V out upon T 2 out upon F, which current is the continuous conduction. Now coming to buck converter for typically solar applications, which used for typically for impedance matching. I mean because for the purpose of maximum power transfer, we have to really keep equivalent to a impedance matching here. I mean like then we can for the PV cell for using this buck converter. So we have output typically R load equal to V out upon V in, and V in equal to equivalent for the source. So I R equivalent to V in upon I in, or V out upon D divided by I out into D, or V out upon I out D square, or R load upon D square. So buck converter makes the load resistance look larger to the source, and you can clearly see from this waveform how really, I mean, a one operating condition where maximum power is 130 watt and we operating the PV cell at 20 module at 29 volt and 4.5 ampere. From maximum power from panel at this solar intensity level, but at the sun condition changes, the maximum power resistance must also change, as you can see. So here the IV characteristic of 6.44 ohm, and when it is really changes, let's say solar intensity changes, we go to another operating condition like you can say 55 watt, and this load resistance value also changes. So we have a load resistance lower than. To draw maximum power 130, connect the buck converter with the parallel and the load resistance, and use the D to modify the equivalent load resistance to by the source so that maximum power is transferred. So I R equivalent to R load upon D square in, or D equal to R load upon R equivalent, and that is under 2 divided by 6.44, that is equal to 0.56. So now the panel needs a ripple free current to stay in the maximum power output. So with wiring inductance react to the current switching with large voltage spike. So we connect here put a capacitor here to provide the ripple current required for opening of the or closing of the MOSFET. So in that way the panel current can be ripple free and the voltage active spike can be controlled. So normally we use a 10 microfarad 50 volt 10 ampere high frequency bipolar and unpolarized capacitor at the input as shown in the red color. So now coming to buck converter design, the worst case component rating of the DC converter typically for this 9 ampere 250 volt 5.6 and 200 250 and current with 16 to 20 ampere. So using here you can call it convert by buck. Input inductor RMS current is 2 pi root 3 I out, and capacitor voltage 1.5 out, and output capacitor current RMS is 1 by root 3 I out, and the diode and MOSFET voltage is 2 in, and diode and MOSFET current is RMS is 2 by root 3 I out. And from this formula you can calculate the different value of typically inductor current 10 ampere, output capacitor voltage 40 volt, and then the output capacitor current 10 ampere, and the diode MOSFET voltage 40 volt, and typically the diode MOSFET current about 10 ampere, likely the worst case condition. So here the values comes from these specification: L equal to 100 and 100 microhenry and capacitor 1500 microwatt 250 5.6 peak, and the we have and diode of 200 volt 16 ampere, MOSFET equal to 250 volt and 20 ampere. And taking here the voltage peak to peak 0.033, that is I allowed upon 4 CFP square for 10 ampere current, 1500 microfarad and 50 kilohertz. So here value given L equal to 100 micron, and typically the rating is the same as it's shown in the previous slide. And for continuous current, what is the inductor comes here. So inductor for here corresponding to value from this typical value, putting 40 volt output voltage, 2 ampere output current and 50 kilohertz. So value comes around 100 microfarad. Now coming to the next converter, we call it DC-DC boost converter, where we have a source input voltage VD, and the ID is the current in the source flowing through the inductor and the MOSFET, diode and capacitor, and the load. So output voltage for continuous conduction of inductor is output voltage Vin upon 1 minus D, and you can call it the boost converter has output voltage larger than the input voltage, and it can also operate it in both mode, continuous conduction mode and discontinuous mode, based on the inductor current. And this boost converter is very extensively used in number of applications as well as part of other converters such as power factor correction converter. Now coming to typically here with the source, inductor, and typically switch and diode and output capacitor with different notation. I mean, when switch is closed, the inductor voltage is the input voltage, and when switch is open, of course the inductor inductor voltage comes in series with the input voltage, and that becomes the output higher than the typically it becomes the output voltage. Is much more unforgiving circuit than the buck converter. So if the MOSFET gate driver is strike in the on position, then there is a short circuit through the MOSFET, and if the load is disconnected from the operation, so I out equal to 0, then the inductor continues to push power right to the very quickly charges C up to high value and blows it out. So before applying power, make sure that your D is at minimum and the load is solidly connected. These are the precautions. So using the KVL and KCL, in the average sense, the average values are here: average inductor voltage is 0 and average capacitor current is 0. That is normally we consider in ideal condition. So find out the input output condition by examining the voltage across the inductor. So here typically we can see here, I mean, when we switch on, so inductor, you can call it the voltage across the inductor is, you can call di by dt equal to V in, or you can call it dIL upon dt equal to V in upon L for switching on period. So diode becomes the reverse bias. The diode is open because the output voltage is more than even the voltage across the switch is 0. So if the switch stays closed, the input is short circuit, and you can call it during really switch off period, the diode conduct, and you have a relation now L dIT equal to V in minus V out upon L, and current decreases because V out is more, so this becomes minus slow. So diode close and assume continuous conduction. So for the operation of 1 minus D seconds. So now coming to average voltage across the inductor, which is 0, VL average equal to D into V in plus 1 minus D into V in minus V out equal to 0, or V out equal to 1 minus D equal to V in, D V in minus D V in. So the input output equation becomes V out equal to V in upon 1 minus D. A realistic upper limit is to boost is the 5 times. So now coming to typically the different modes of operation. When switch is closed, you can see diode is open circuit and how the inductor current and typically your inductor voltage is there across. So VL equal to switch on to VD, and that is equal to dIL upon dt, or dIL upon dt equal to VD upon L, or dIL upon dt equal to delta IL upon dt into delta I upon D into T, and dIL upon dt, that is VD upon L, or delta IL close equal to VD into dt upon L. So now typically when the switch is off, diode conducts. During that period, you can see the waveform in second mode. I mean during 1 minus D into T. So VL equal to VD minus VO equal to L di upon dt, or dIL upon dt VD minus VO upon L, and dIL upon dt delta IL upon delta T equal to delta IL upon 1 minus T into T. So dIL upon dt becomes VD minus VL upon L, and delta IL opened is VD minus VL into 1 minus D into T divided by L. So now coming to during on period, switch is closed and diode is reverse bias, resulting in input voltage across the inductor as VL equal to V in equal to L dIL upon dt, or dIL upon dt equal to V in divided by L. So from this equation, it can be observed that the rate rise of the current is constant and the inductor current rises linearly, and change in the inductor is calculated as delta IL upon delta T equal to delta IL upon dt, or V in upon L equal to delta IN on equal to V in dt upon L. So when the solid state switch is made off, the current flows through the inductor and cannot change instantaneously. Therefore, it flows through the diode considering the output voltage constant, and the across voltage across the inductor is VL equal to Vin minus VO, or equal to L di upon dt, or dIL upon dt equal to VO minus Vin by L. So during off period 2, the rate change of current is constant and the current is decreasing linearly. As this rate is negative due to VO greater than Vin, hence the change in inductor current during off period is as delta IL upon delta T equal to V delta IL upon 1 minus D into T, that is Vn minus VO upon L, or delta IL equal to Vn minus VO into 1 minus D T divided by L. So under steady state condition, total change in the inductor current is 0. Therefore, it is stated delta IL upon plus delta I of equal to 0, or V in D T upon L plus V minus VO into 1 minus D into T upon L equal to 0, or V in D plus 1 minus D equal to VO minus 1D, and from which we get VO equal to V in upon 1 minus D as a transfer function for ideal condition. Now, alternately, it can be derived from the fact that the average voltage across the inductor is 0 over a period. So, VL upon T, that is on period, equal to V in into dt plus V in minus VO into 1 minus D T equal to 0, or this becomes VO equal to V in upon 1 minus T. So, which is same as the previous equation derived for expression output voltage. So, from this relation between input and output voltage, it may be summarized that the output voltage can be boosted only but cannot be decreased. So, average inductor current can be calculated from the power relation as the power losses are neglected in an ideal converter. P n equal to V in I n equal to P O equal to V O I O, or that is equal to VO upon R, or VO square upon R. So, since IL upon IN, therefore IL equal to VO square divided by R P in, or IL equal to V in upon in bracket 1 minus D square into R. So, the maximum and minimum current in the inductor can be obtained from average current and current ripple. So, I max equal to IL plus delta IL by 2, or equal to V in upon 2 V in bracket 1 minus D square R plus V in dt by 2L, or this IL max equal to V in bracket 1 upon 1 minus D into TR plus dt by 2L, or I minimum is IL minus delta IL by 2, that is V in bracket 1 minus D square into R minus V in dt by 2L, and where moreover IN equal to IO into 1 minus D, from which VO equal to V in IN. However, for boundary condition in CCM and DCM, I minimum is 0, from which the maximum inductance for critical inductance can be calculated. I minimum equal to 0, V in equal to divided by 1 minus D square R plus minus V in dt divided by 2L, or IL minimum is D in bracket 1 minus D square R divided by 2F. So, here also you can call it minimum inductance for boundary condition becomes a function of switching frequency, of course due to load as well as due to check. So, now the output voltage ripple can be calculated due to discharge of capacitor caused by load current during the on period. The on period, the source is not connected to load, only capacitor is providing the output. So, delta V equal to delta Q upon C, that is 1 upon C I0 dt, or I0 DTC, or equal to VO dt divided by RC, or V delta V upon V0 equal to dt upon RC, or dt divided by TA, that is TA is the time constant RC. So, you can find out the ripple, from ripple voltage, or even from this you can find the capacitance also. So, from with this the value of capacitance can be calculated, or that is C equal to V into dt upon delta V upon R. Similarly, the value of inductor can be calculated for given ripple current, L equal to V in dt plus divided by delta IL, or V in D divided by F delta IL. So, that is L equal to V O D 1 minus D divided by F delta IL. So, it means the inductor also here becomes corresponding to inversely proportional to switching frequency. So, here also if you increases the frequency, you can just clearly see that the capacitor also reduces as well as inductor, because capacitor relation is delta T. So, you can say T becomes 1 upon F. So, in both cases inductor and capacitors are inversely proportional to switching frequency. So, as you increase the switching frequency, the element value decreases for this L and C. These are the typical waveform boost converter in CCM, with the input voltage, input current, and output voltage, output current, with the inductor voltage, inductor current, then the switch voltage, switch current, diode voltage, diode current. So, now coming to non-ideality in the typically in boost DC-DC converter. So in the analysis carried out so far, all the components are considered ideal. In practice, an inductor has a small resistance RL, and voltage across the device and diode cannot be neglected, especially when the operation is at very low output voltage level. So VL on equal to IL on to RL or equal to V in minus VT, transistor drop order, where VT is the voltage across the switching device during the conduction. So voltage across the inductor during the off period is VL of equal to IL of to RL or equal to V in minus VO minus VD, diode drop. So the average voltage drop across the inductor is VL equal to IL RL equal to IN into RL or equal to V in minus VT into D plus V in minus VO minus VD divided into 1 minus D, or V equal to 1 minus D plus IL in RL or equal to V in minus DVT minus VD and into 1 minus D. So you can call it input current can be expressed approximately IL equal to IN, I upon 1 minus D or V upon R 1 minus D. So from these equations, output voltage equal to V in minus DVT minus 1 minus D VD divided by 1 minus D plus RL divided by R 1 minus D. So here you can see in case in ideal condition, the output voltage certainly depends on not only duty cycle and input voltage, but it also depends on transistor drop, diode drop, and inductor resistance, as well as of course the load resistance. Where R is the load resistance, R is the resistance of inductor, PD is the voltage across the diode while conducting, and value of output voltage is certainly lower than the ideal condition, V equal to N by 1 minus D. The effect of equivalent series resistance of the output capacitor can be considered similar to the case of buck converter. So the average, coming to boost DC-DC converter analysis in DCM, so the average voltage across the inductor is now VL into T equal to V in into dt plus V in minus VO into D1T equal to 0, where D1T is the period of diode conduction which is lesser than 1 minus D into T. So where D1T is the only part of 1 minus D to T of, and is less than the T of during for the discontinuous mode of conduction. So solving this is equal to VO equal to V in D plus D1 divided by D1 to calculate the value of D1 in terms of other parameters. The average diode current is now ID equal to I max D1T divided by 2T equal to, that is I max D1 by 2. So the maximum inductor concept during this period is I max equal to I delta I L, and that is V in dt upon L. So from these equations we can find out average diode current, ID equal to I average, IO average equal to VOR into V in equal to V in dt by 2L, and solving this equation for D1 becomes equal to 2 VOL divided by V in into dt, and from which we can find out VO upon V in equal to in bracket 1 plus under root 2d square RT upon L divided by 2. It means it depends not only duty cycle, this output voltage and input, it also depends on the load resistance, as well as it depends on switching frequency and inductor value. So it is much nonlinear relation between input and output voltage than continuous conduction mode. And these are the typical waveform for discontinuous conduction mode. As you can see here, the inductor current, input current, that is the inductor current becomes discontinuous, and all the waveforms like input voltage, input current, output voltage, output current, inductor voltage, inductor current, and switch voltage, switch currents, and diode voltage, diode current are shown. Now coming to the third category of converter called buck boost converter, buck boost DC-DC converter, where we have a source PD with the device, switching device, then inductor, diode, and capacitor, and load. Of course, the drawback of this converter is the output voltage polarity is reverse, as you can see, because of diode conduction. But the advantage is that you get buck and boost operation with the same number of component as in buck converter as well as in boost converter. One switch, one diode, one inductor, and of course output filter capacitor. So buck boost converter is very widely used converter because it is capable of bucking, boosting the input voltage to obtain regulated DC output voltage. And you can see both the modes when typically switch is on. Of course, normally the input filter is used. So when the switch is on, the inductor short circuited in the input voltage and capacitor supply the load, as you can see. And when the you can say switch is off, the diode conducts and feed the energy to the output capacitor like here, and you can see clearly the waveform. Even during the DCM mode also. So you have you can call it device conduct, then inductor conduct, diode conducts, and typically you have a output voltage and inductor current. So that is the third mode, where the diode and device both discontinuous, and you will have a DCM mode. Typically none of the two have the current as third mode in DCM. So now coming to analysis of this buck boost DC-DC converter. During the on period, the voltage across the inductor is VL equal to Vin, that is L divided upon dt, that is similar to the boost converter, or DIL upon dt Vin upon L, and the change in current for on period is delta IL on equal to Vin dt upon L. And during the off period, switch is open and diode is conducting, the inductor voltage is VL equal to VO equal to L DIL upon dt, or DIL upon dt equal to VO upon L. So rate change of current can be written as delta IL upon dt equal to delta IL 1 upon 1 minus d into t VO upon L for CCM mode, and delta IF equal to VO into 1 minus d t divided by L. So under steady state total change in the inductor current is 0. So delta IL plus delta IF equal to 0. So V in dt upon L plus VO 1 minus dt upon L equal to 0. So VO equal to V in into minus d upon 1 minus d. The minus sign here represents the typically your output voltage polarity is reversed. So alternately it can be derived from the fact that the average voltage across the inductor cycle is 0. So VL equal to V in d plus VO 1 minus d equal to 0, or VO upon V in equal to minus d upon 1 minus d. So in case of lossless system, PO equal to V into IO equal to, that is VO square upon R of P in equal to V in IN, and from the voltage and average input current is, so IN equal to D into IL, and V in IL D equal to VO square R, and from this equation the average inductor current is IL equal to VO square in bracket V in RD divided by PO upon V in to D, or equal to V in D divided by in bracket R 1 minus D square. So from this equation, the inductor maximum minimum current can be defined as I max equal to IL plus delta IL upon by 2. So V in equal to V in divided by R in 1 minus D into 2 plus V in dt upon IL, or I minimum equal to IL plus delta I minimum, that is V in divided by R 1 minus D into 2 minus V in dt, typically IL. So for boundary condition between the CCM and DCM, the value of the critical inductor can be calculated I minimum equal to 0. So L minimum equal to 1 minus D square R upon LF. So this critical inductance minimum is affected by switching frequency, load and duty cycle as evident from this equation. However, the inductance for given current ripple can be calculated as L equal to V in delta dt upon delta IL, or equal to V upon 1 minus D into T into I delta IL. So in lossless system, the power balance IN equal to VO, V in IN equal to VIO. So IN equal to IO D upon divided by 1 minus D. So now coming to buck boost converter operation in ripple, output voltage ripple in continuous conduction mode. So similar to the boost converter, the output capacitor discharged to the load during the on period, and the voltage ripple can be calculated as delta V0 equal to delta Q upon C, that is 1 upon C into IO into dt, indication IO dt upon C, or VO dt upon RC, and per unit voltage ripple is defined from this. So delta VO divided by VO equal to dt upon RC, or equal to D upon RCF, or equal to dt upon TA, where TA is RC time constant for the load resistance, R and the output capacitor, and F is the switching frequency of the converter. So from the above equation, the output capacitor value C can be calculated for a given voltage ripple. C equal to dt V0 upon delta VR, or dVO upon delta VRF. So these are the typical waveform for continuous conduction mode of the simulated waveform for buck boost converter, which starting from input voltage input current, output voltage output current, then inductor voltage inductor current, switch voltage switch current, diode voltage diode current. Now coming to non-ideal conditions in buck boost converter. So in the previous analysis, all the components are considered ideal. So in practice, an inductor has resistance RL, and semiconductor devices have the voltage drop while conducting, which cannot be neglected, especially low voltage converter. So the voltage across the inductor during on period is VL on minus IL on RL equal to V in minus VT. So where the VT is the voltage across the switching device, and conduction, R is the resistance of the inductor. So the voltage across the inductor during off period is VL of equal to IL of into RL or equal to minus Q1 minus VD. So the average voltage across the inductor is VL equal to IL RL equal to Vn minus VD, Vt into D plus 1 minus T into in bracket minus VO minus VD, or VO in bracket 1 minus D plus D square RL upon 1 minus DR, or equal to Vn into D minus VTD minus 1 minus T VD, and VO equal to Vn into D minus VTD minus 1 minus D VD, and in bracket 1 minus D square RL upon 1 minus D R. So you can see output voltage here depends on your transistor drop, device drop, diode drop, and load inductor resistance and load resistance. Like however, in case of ideal condition, this VO equal to V in D into 1 minus D. The effect of ESR of output capacitor may be considered similar to case of buck converter. So now the operation of buck boost converter in discontinuous conduction mode. The average voltage across the inductor is 0. So T equal to V in dt equal to minus VO D1T equal to 0. So where D1T is a part of the off period during which the diode conducting, but always less than the off period, that is 1 minus D into T. So solving this equation, we get VO upon Vn equal to D upon D1. From the relation Pn equal to PO, I becomes IO upon In equal to D1 upon D. The average inductor current is IL equal to Vn into dt in bracket D plus D1 divided by 2L, and the diode current average is ID equal to IO average VO upon R, that is I max D1T divided by 2T, and maximum current during the on period delta IL equal to I max P in dt upon L. So the value of D1 from this equation is D1 equal to 2 VO L divided by V in dtR. So the waveform of this buck boost converter in DCM, you can clearly see the input current, discontinuous, and output current, and inductor voltage and inductor discontinuous current, and switch voltage, switch current, and out voltage out. Now coming to another category of buck boost converter, that CUC converter. The CUC has invented it. So here we have a device, supply voltage, then inductor, then switch, capacitor, diode, inductor, and capacitor, and load. Of course, we call it the C1, C2 and L1, L2, and the ideal condition, the output voltage dVd, Vn upon 1 minus D. Here also this is a buck boost converter because of D upon 1 minus D. There again two modes are there. When diodes are when the device is switching into conducting, you can see how the current flows through the inductor switch and how the current flows typically in the output capacitor because of the capacitor charge and output. And similarly for doing when switch of diode conducts, how the current flows from the source and the current flows the output capacitor or the load. Like so, you can clearly see the waveform also the input current, which is input inductor current, that remain continuous, and typically your output inductor current. Of course, in DCM it can go discontinuous mode, but otherwise it would remain normally in continuous conduction mode. So in continuous conduction mode, we have a 2 mode. Discontinuous conduction, we have a 3 mode. And this is the typically 3rd mode when diodes, none of the 2 are conducting, like typically. So here you can clearly see how this opens. Now coming to the CUC converter analysis under ideal condition, the average voltage across the inductors are 0. So therefore the energy transferring capacitor voltage is Vc1 equal to Vn minus Vo. When the solid switch is on, the diode is off, and the capacitor current is IC1 on equal to minus IL2. And with the switch off, the diode is on, and capacitor current is IC1 off equal to IL1. And so in lossless system, the input output power equal. So VO equal to IO equal to V into IL2, or Vn equal to Vn in In equal to V into IL1, or IL1 upon IL2 equal to V upon Vn. So for periodic operation, the average current in the capacitor is 0. So IC1 on equal to dt plus IC1 off 1 minus t into t equal to 0. So I putting a value, it's IL2 to dt plus IL1 1 minus d into t equal to 0, or IL1 upon IT. IL2 is d upon 1 minus d, and from the previous and this equation, it becomes V upon Vn equal to d upon 1 minus d. So that clearly says the buck boost operation. So there is an alternative method for device to derive this relation, which is based on the integral of voltage across the inductors 0. So L1 Vn dt plus Vn minus Vc1 1 minus d into t equal to 0, or Vc1 equal to Vn upon 1 minus d, and the voltage across inductor L2 Vl1 minus Vo dt plus minus v upon 1 minus d into t equal to 0, or vc1 equal to v upon vd, taking vc1 both the relation, so we can get v upon vn equal to minus d upon 1 minus d. And now output voltage ripple, that is current through the output capacitor, is IC2 equal to IL2 minus IR, and from the waveform the charge is for charging, from the charging current q equal to delta c v0, or delta q equal to delta v, or delta v equal to delta q upon c, and delta v equal to half t by 2 delta IL, and that becomes t delta IL2 by 8, and it results in the ripple in voltage delta VL equal to T delta IL by 2 divided by 8 C2. So ripple voltage across the capacitor is computed from off period. So delta VC1 equal to 1 upon C is your dt to T IL1 dt equal to IL1 upon C into 1 minus D into T, or equal to V in D square by in bracket RC1 F 1 minus D, and delta VC1 equal to V T upon RC1 F. The value of energy transfer capacitor can be calculated from the given voltage ripple. C1 equal to V0 D divided by R delta VC1 F, or change in inductor current IL1 is same as IL1 equal VL1 equal to Vn equal to L DIL upon dt, or change in input conductor current delta IL equal to Vn delta dt upon L1, and that is equal to Vn into dt into L1F. So similarly, voltage across the inductor L2 during on period is your VL2 equal to VO plus Vn minus VO, or equal to Vn, and that is L L2 upon dt. So the rate change in IL2 as delta IL Vn dt by L2, and Vn dt upon L2F. For continuous current in the inductors, the average current must be greater than the one half of the change in their current. So minimum value of inductor for continuous current is L1 of L1 minimum equal to 1 minus d square R upon 2 df, and L2 minimum is your 1 minus d R upon 2f. However, the value of inductor can be obtained from the equation. For a given current ripple current, L1 equal to V in d upon delta I1f equal to 1 minus d delta V upon delta IL1f, and L2 equal to V in delta dt divided by delta IL2f, or equal to 1 minus d V upon delta IL2f. So typical waveform for continuous conduction mode of this Cuck converter is input inductor current, which you can say continuous, output voltage output current, and inductor voltage inductor current, which is continuous, and output typically inductor voltage and inductor current, and capacitor voltage energy transfer capacitor voltage, then switch voltage switch current, and diode voltage diode current. Now coming to operation of Cuck converter in DCM, based on the alternate method to devise the input output voltage relation, which is based on the integral of the voltage across the inductor L1 equal to V in dt plus P1 minus Pc1 dt1 t equal to 0, and Vc1 becomes here V in into d plus d1 into d1, and L2 Vc1 minus Vo into dt plus minus Vo into dt1 t to 0. So Vc1 goes from this relation equal to Vo in bracket V d plus d1 by d. So equating both Vc1 relation here, we get from V upon Vn equal to d upon d1, and for power balance PO equal to in IO upon I in, that becomes d1 upon d. So average current in the inductor is IL1 equal to IN V in dt d plus d1 divided to IL1 plus I, and IL2 equal to V in dt d plus d1 divided by 2 L1 minus I. So from these two equations, we can get IL1 plus IL2 equal to V in dt plus d upon d1 plus 2L, and where L equal to L1 L2 divided by L1 plus L2 by combination of L1 and 2, and from this IL1 d1 plus d1 upon d equal to V in dt in bracket 1 plus d1 upon d into d upon 2L, or IL1 equal to d square t V in upon 2L, and from this relation equivalent resistance R is Rn equal to V in upon In, that is V in IL1, that is 2L divided by d square t, and from power relation IN Rn square IO square R. So that becomes typically V upon Vn equal to IO In upon IO, or V upon IN equal to IN upon I0, or equal to under root R upon Rin, or under root R d square t upon 2L, or d upon under root 2L R t. So you can clearly see how this your typically the parameters are involved in output output relation, and where from which we get T1 equal to under root 2L upon RT. And these are the typical waveform for discontinuous current mode, especially for the output inductor current. As you can see, output inductor current is discontinuous and remaining waveforms typically. So now coming to another category of buck boost converter that called SEPIC, single-ended thymodic inductance converter. The advantage is that output polarity voltage is not changed, but the disadvantage now the output, the capacitor charge similar to the like a boost converter. So where VO equal to D upon VD upon 1 minus N, but the number of component is the same as the converter. So we have L1, L2 and C1, C2. So the input relation similar to like a here inductor, and typically we have a MOSFET, then capacitor, inductor 2, L2 and then diode capacitor at load. So you can just see here typically the in this case also SEPIC, which we call single-ended primary inductance converter. So circuit is more unforgiving than the boost converter because the MOSFET and diodes voltage and currents are higher. And before applying power, make sure that your D is at the minimum and the top load is solidly connected. Because a buck boost converter, D should be 0 at the start, so that output voltage is starting from 0. So now coming to with the KVL and KCL, in this average sense here, the KVL shows VC1 equal to V in. So interestingly, no average current passes from the source side through C1 to the load side, and here this is the called DC-DC converter. And you can see KVL that is shows here when switch is closed, it's a VD equal to minus V in upon plus V out, so that diode is open. Thus the C is providing the load power when switch is closed because diode is reverse bias. Similarly, in case of an, you can see IL1, IL2 ramping up, charging, and C1 is charging L2 and C is discharging across the load, as you can see in the mode. And similarly, typically when you can call it the switch is open, so typically diode is conducting, so C1, C2 are charging, L1, L2 are discharging. KVL shows VL1 equal to V out. The input output equation comes from recognizing the average voltage across L1. So VL1 average equal to dV in plus 1 minus D into minus V out equal to 0. So V out 1 minus D equal to dV in, and which gives the relation V out equal to dV in upon 1 minus D. The voltage can be stepped down or stepped down. That's why it's called buck boost converter. Typically coming to the relation, what is the compared with this? Here energy storage component, capacitor does not carry load current. In both converter, isolation can be easily implemented and polarity is reverse, so voltage can be stepped or stepped down. So in a steady state operation, the waveforms of the voltage across the inductor L1, L2 repeat from one time period to the next period. Therefore, the integral of inductor voltage for the period must be 0. So voltage across L1 equal to V in dt in plus V in minus VC1 minus VO into D1 minus D into T equal to 0, and across the L2 minus VC1 into dt plus VO 1 minus D into T equal to 0, from which we get VC1 equal to VO upon 1 minus D upon D, and substituting the value VC1 from in the another equation, so we get Vn upon V out equal to 1 minus D upon D plus 1 or into 1 minus D, or VO 1 minus D upon VO, and from which we get VO upon Vn equal to D upon 1 minus D, demonstrating that it's also buck boost converter. So the change in the, you can call it the change in input inductor current delta here is calculated from the conduction condition when the solid state switch is on. So VL1 equal to V equal to L1 di1 upon dt, or change in the input inductor current delta IL1 delta IL1 equal to V in dt divided by L1 equal to V in d upon L1f, and the value of inductor L1 for the given ripple current can be calculated. L1 equal to V in dt upon delta IL1 f, and similarly the rate change of current of second inductor L2 during off period is VO equal to L2 dIL2 upon dt, or change in this inductor current is delta IL2 VO 1 minus D into T upon L2, or equal to VO 1 minus D divided by L2f. So the value of inductor L2 for the given ripple current IL2 can be computed. L2 equal to VO upon 1 minus D divided by F delta IL2. The ripple voltage across capacitor C1 is computed from period. So delta VC1 equal to 1 upon C dt IDT, or that is IL1 1 minus D T1 upon C1 and VO dt on RC1 F, and the value of capacitor C1 can be calculated for ripple. So C1 equal to V0 D upon RF delta VC1. So this output voltage ripple delta VC across the capacitor C2 can be calculated during the on period. So delta VO equal to delta VC2 equal to delta Q upon C, that is IO dt upon C or equal to VO dt upon RC. So calculate value of output capacitor for given voltage ripple can be calculated. C2 equal to dV0 divided by RF delta V0, and that is equal to dt in bracket R delta V upon V0. So for calculation of inductor values for the boundary condition between CCM and DCM, the inductor currents to maintain continuous current, the average current in the inductor must be greater than half the change in their current. So minimum value of the inductor for just CCM L1 minimum equal to V in minimum D upon 2 I in F equal to R 1 minus D square upon 2 DF, and minimum, L2 minimum is VO equal into 1 minus D upon F in bracket F into delta IL2 maximum. So these are the typical waveform in continuous conduction mode of SEPIC DC-DC converter. As you can clearly see here, we have input voltage, input current, output voltage, output current, then inductor, input inductor current, output voltage, output inductor current, and then capacitor voltage, energy transfer, and switch voltage, switch current, and diode voltage. Now coming to the operation of SEPIC converter in discontinuous motor current mode, the relation between input output voltage can be derived as L1 equal to V in dt plus V in minus VC1 minus V into D1T equal to 0, and L across L2 minus VC1 dt upon dt plus VO D1T equal to 0, or from which we can get VC1 equal to VO D1 on D, and substituting the value of VC1 from this results in V in bracket VD plus D1 equal to VO 1 plus D1 upon D into D1. So from power balance, we have PO equal to V in equal to IO upon IN equal to D1 upon D equal to IL1 equal to IO D upon D1. So the average in current in the inductor L1 is IL1 equal to IN equal to V in dt in bracket D1 plus D1 divided by 2 IL1 plus I, and average current in the inductor 2 is IL2 V in dt in bracket D plus D1 divided by 2 IL2 minus I. So adding IL1 I2 results in IL1 plus I2 equal to V in dt in bracket D plus D1 divided by 2L, and where L equal to L1 L2 upon divided by L12. From these equation, the capacitor average current is for equivalent circuit is IC1 equal to I plus IL1 minus I into D divided by D1 plus D plus D1 minus IL2 plus I D upon D plus D1. So since capacitor C1 blocks the DC current, the average value of capacitor current is 0, and from this relation IL1 upon IL2 equal to D upon D1, and from this equation IL1 is equal to IL1 to 1 plus D1 upon D equal to Vn dt D plus D1 divided by 2L, or IL1 equal to D square Vn into T divided by 2L into In, and from this the input resistance Rin equal to Vn In equal to D square T upon 2L, and from power relation In square Rin equal to IO square R, and V upon Vn In equal to In upon I0 under root R upon Rin equal to under root RD square RT divided by 2L equal to D under root in bracket 2L divided by RT, or D1 equal to under root 2L divided by RT. So the waveform in DCM of this SEPIC converter, where the output inductor is made to operate in discontinuous mode, you can see here. Now coming to Zeta converter, this is also another category of buck boost converters. So here we have output again voltage relation in continuous conduction mode D into V in upon 1 minus D, that V in with the switch, then the inductor and capacitor, and diode, inductor and capacitor. The again advantage here, output polarity is not reversed here, but input current is continuous, output current input current is continuous, output current is continuous, and you can see the clearly typically the mode here, when the switch is conducting, when diode is conducting, and when none of the two conducting. Three modes take place here. So coming to typically it is buck boost converter and has only one solid state switch under the steady voltage across the inductor L1 L2 vary for one time period to the next period, and the integral of the inductor voltage must be 0 for a period. So voltage across the inductor L1 Vn equal to dt minus Vc1 minus d to t equal to 0, or from this relation we get Vc1 equal to Vn into d divided by 1 minus d, and the voltage across L2 is in minus Vc1 minus v into dt minus equal to minus Vo into d 1 minus d into t equal to 0. So from which we can get putting a value of this Vc1 from first and second, we get the V equal to Vn into d upon 1 minus d, and the charge in the input inductor current, change in the input current IL1 is calculated from the period. So you can call it VL1 equal to Vn equal to LDI by dt upon d upon dt. So delta IL upon V in dt upon L1, or V in dt upon LF FL1, or the value of inductor L1 can be calculated V in upon V1D divided by F delta IL for a given ripple current. So similarly, rate change of the current IL2 in the output inductor can be calculated during off period. So V equal to L2 IL2 dt. So IL delta IL2 equal to VO minus 1 minus D to dt upon L2, or VO 1 minus D divided by FL2, and output inductor L2 equal to VO 1 minus D divided by F delta IL2. So ripple voltage across the capacitor is calculated from the on period. So delta VC1 equal to 1 upon C to I dt, and that is IL2 dt upon C1, that is IO dt C upon C1, and that is equal to VOD divided by RCF. The value of capacitor C1 can be calculated. Given word C1 equal to VOD divided by RF to delta VC1. So output voltage ripple across the capacitor C2 can be calculated from the output inductor current ripple. Delta IL2 is responsible charging the current for T by 2 period. So delta VC V0 equal to delta Q upon C2, or 1 by C2 into half into delta I2 by 2 into T by 2, or delta V equal to T V0 1 minus dt divided by delta 8 L2C, or delta V upon V0 upon V delta V upon V0 to 1 minus D divided by 8 F square L2C. The value of C2 capacitor is equal to 1 minus D T square divided by 8 L2 delta V0 upon V0. And these are the typical waveform in conduction mode of the Zeta converter for input voltage, input current, output current, inductor voltage and current, output voltage, output inductor current, and capacitor voltage, and switch voltage, switch current, and out voltage out. So now coming to the operation of Zeta converter in discontinuous current mode. So for boundary condition between continuous and discontinuous mode of inductor current and the capacitor voltage, the maximum ripple in this quantity must be double the average value. The critical value of L1 is L1 minimum. So V in dt1 divided by 2 IL1. And similarly, the critical value of L2 is L2 minimum equal to VO 1 minus D into T upon 2 IA0, that is equal to 1 minus dr upon 2f. So VC1 is the average capacitor voltage. The capacitor ripple voltage is equal to delta VC equal to 2V0, and critical value of C1 is C1 minimum equal to V0D divided by RF into 2V0, or equal to D upon 2FR. Similarly, the critical value to calculated from L2 minimum. So C2 minimum is 1 D divided by 16 L2 F square, or 1 upon 8 FR. So the relation between input voltage can be derived from voltage across L1 L2. So L1 voltage across L1 is V into dt plus minus VC1 d1t, or VC1 comes here equal to V1 d upon d1, and from L2 is a V in plus VC1 minus VO dt plus minus VO d1t, and substituting the value, then it comes V in d in bracket 1 plus d by d1 minus VO in bracket d plus d1 equal to 0. So it comes V upon Vn equal to d upon d1, and for power balance P equal to I upon In. So d1 upon d, and that is IL2 In, that is d1 upon d2. So the average inductor current in the L1 is IL1 in dt in bracket d plus d1 by 2 L1 minus I, and average current in the inductor 2 is IL2 in dt in bracket d plus d1 divided by 2 L2 plus I. So adding IL1 to IL1 plus IL2 is equal to V in dt in bracket d plus d1 divided 2L, where L equal to L1 L2 divided by L1 2. So the waveform Zeta converter in DCM, you can clearly see here how the input voltage, input current, output current, and the input inductor current, output voltage, output inductor current, then capacitor voltage, energy transfer capacitor voltage, and the you can call it switch voltage, switch current, and out voltage out. Now coming to buck half bridge DC-DC converter, here you can see the relation comes from the circuit V equal to V in bracket 2D minus 1 divided by 2, and here in steady state condition, waveform of inductor L and the capacitor current and voltage repeat from one period to other. So therefore the integral of the inductor voltage for the one period must be V in by 2 minus VO into dt, and in bracket 1 minus V in by 2 minus VO in bracket 1 minus d into t equal to 0, from which we get the relation V equal to V in 2d minus 1 divided by 2. So this converter is capable of reversing the output voltage and thus known as bidirectional bipolar converter. It can be observed from this sequence that D is vary from 0 to 0.5, then the polarity of output voltage is of opposite polarity of the input. If D is your 0.5 to 1, then the output voltage of same polarity as the input voltage. So now coming to change in the inductor current can be calculated as a dIL upon dt equal to in bracket V in minus by 2 minus V upon L, and the change in the inductor current is your delta IL equal to 0.5 V in minus VO dt upon L, or equal to VO into 2 d square T divided by 2d minus 1 into L. The value of inductance can be calculated from L equal to 0.5 VL V in minus VO divided by delta V in, or that is equal to 2d square divided by 2d minus 1 F into delta IL, and per unit value can be calculated of current, that is delta IL upon IL, that is delta IL upon I0, that is 2 V0 RD square divided by 2d minus 1 F E0L, or equal to 2 RD square divided by 2d minus 1 FL. So similarly the ripple voltage across the output capacitor, so delta V equal to Q0 C divided by half T by 2 delta IL by 2 C, that is equal to T delta IL by 8 or 2d square VO T square divided by 8 2d minus 1 into L, and the per unit ripple voltage is delta V divided by VO equal to d square T square divided by 4 in bracket 2d minus 1 into LC, and output capacitor value from this is C equal to T square VO divided by 4 2d minus 1 L delta VC. So these are the typical waveform of simulated waveform of this typically of buck boost half bridge converter. And coming to now full bridge DC-DC converter, that is V equal to D into VT, as you can see in the circuit. So under the steady state condition, voltage and current waveform are periodic across the inductor and capacitor, therefore the integral of inductor voltage over the current period must be 0. So V in minus VO equal to dt minus VO 1 minus T into T equal to 0. So it's simplified VO equal to dV. So however it is obtained by switching diagonal switches S1 S2, and reverse voltage polarity can be obtained by switching diagonal switch S3 S4 if the unipole one switch S1 S2 is made on and off and other switch is left on. So the rate change of the in the inductor current can be calculated from the condition dIL upon dt equal to minus VO upon L, and the change in inductor current delta IL can be calculated as delta IL equal to VO 1 minus d T upon L, and the per unit value of inductor current can be calculated delta IL upon IL equal to delta IL upon I0 equal to V0 1 minus d TR upon L into V0 equal to 1 minus dR upon FL, and the inductor value can be calculated L equal to V0 1 minus d T upon delta IL, that is VO 1 minus d divided by delta IL into L. So now ripple voltage across the capacitor can be calculated, that delta V0 equal to delta Q0 divided by C half T by 2 delta IL1 by 2 by C, so that comes T delta IL upon 8C, or equal to VO 1 minus D divided by L F square LC. So per unit ripple voltage as delta V upon V0, that is in bracket 1 minus D in bracket 8 F square LC. The output capacitor value can be calculated for a given voltage C equal to VO 1 minus D divided by 8 F square L into delta V. So minimum critical inductance for boundary condition basis ACM DCM is L minimum VO 1 minus D divided by 2 IO upon 2 IOF, or equal to 1 minus D R upon 2F. So critical capacitance value for output V equal to 2V, we calculate C minimum 1 minus D divided by 16 F square L. So similarly the analysis and design for full bridge converter can be carried out in bipolar switching control method, and these are typical waveform for buck full bridge buck DC-DC converter. Now coming to boost half bridge DC-DC converter, where we have a coupled inductor in between, the two switches, and that inductor makes this as a current source, so input current source, and we get the buck boost operation. So this converter provides the reversible polarity of output voltage with the change of duty cycle of the solid state switch devices as the steady state condition. The waveform of capacitor, inductor voltage and currents are periodic in nature in repeated waveform. So therefore the integral of inductor voltage of midpoint capacitor voltage coupling must be Vn by 2 minus Vo equal to dt equal to minus Vn by 2 minus Vo equal to 1 minus d into t. It results in input voltage less than Vo equal to Vn divided by 2 in bracket 2d minus 1. So it can be seen from the equation that if d varies from 0 to 0.5, then the polarity of output voltage is opposite to input voltage, and if d varies from 0 to 0.5, then the output voltage is of same polarity as the input voltage. So the change in inductor current can be calculated delta IL upon dt equal to Vn minus 2 minus Vo divided by L, and thus the change in inductor current is as delta IL to 0.5 Vn minus Vo into dt upon L, that is equal to 2 Vo d minus 1 into d by FL. and the per unit change in the inductor current is as delta IL upon L equal to delta IL upon I0 2V0 t minus 1 dr upon FV0 L equal to 2d minus 1 dr upon FL. So if the value of inductor can be calculated from that is equal to L into 2V0 d minus 1 upon d into d divided by F delta IL, and the ripple voltage across the output capacitor can be calculated as delta V0 to delta Q0 by C, that is half T by 2 delta IL by 2 divided by C. So that is equal to T delta IL upon 8C or equal to 2d minus 1 d V0 divided by 8 F square LC. So per unit triple voltage will be delta V0 upon V0, that is equal to d1 minus 1 d in bracket 4 F square LC, and the output capacitor for a given value of triple voltage C equal to d minus 1 into dV divided by 4 F square L delta V. And these are the typical waveform of boost half bridge DC-DC converter. Now coming to boost full bridge DC-DC converter, as you can see, if you put a inductor in series with the inductor of input, it becomes a current source, and now this relation becomes V equal to V in by 1 minus D. So now under the steady state condition, voltage and current waveform of the are periodic in nature, therefore the integral of the inductor voltage over the one period must be V in into D plus V in minus VO equal to 1 minus D T equal to 0, simplified to VO equal to V in minus D. This control during on period, all switches both are on, one lag mode on, and during off period only two diagonal switches are S1 S2 for positive and S3 S4 for negative. Polarity of output voltage are made on. So the rate change of the inductor current is calculated from the on period as DIL upon DT equal to V in upon L. So the change of inductor current is calculated from this equation delta IL upon V in DT upon L, and the per unit current ripple in the inductor is delta IL upon IL equal to delta L upon IN equal to VO D into 1 minus DT divided by L I0 divided by 1 minus D and equal to 1 minus D square D RL upon 2 upon FL, and the boost inductor value can be calculated as L equal to V in DT upon delta IL equal to V0 D1 minus T divided by F delta IL. So now ripple voltage at the output capacitor can be calculated delta V0 equal to delta Q0 upon C, and that is I0 dt upon RC, that is VO dt upon into RC equal to V dt upon divided by FRC. And the per unit ripple voltage can be calculated that delta V upon V0, that is dt upon RC, that is D upon RCF, and the value of capacitor output capacitor can be calculated from this equation C equal to delta V0 D divided by F R delta V. So minimum critical inductance for boundary condition between CCM and DCM is delta IL equal to 2V, that is equal to 2IO upon 1 minus D. So L minimum is V0 into D 1 minus D square upon F into 2I0, and that is equal to 1 minus D square dr upon 2I. And critical question for output voltage with delta V equal to V0 is calculated C minimum equal to D upon 2 FR. Similarly, the analysis and design of both boost converter bipolar switching control can be carried out for bipolar output. And these are the typically boost full bridge DCM converter simulated waveform in CCM mode. Now coming to Leo DC-DC buck boost converter, as you can see the relation here, that V equal to D upon VD upon 1 minus N. As you can see here, the input along with the input filter, we have a now switch inductor, then diode, capacitor, and typically the inductor and output voltage. So you can see typically three mode: when the switch is on, when typically the diode is on, and when your both are off, and typical waveform. And these are the typical other kind of Leo converters, other configuration like with the elementary circuit which we have discussed earlier, then self lift and relift and double lift. So for taking a basic circuit of Leo converter, so under steady state voltage across the inductor L1 L2 repeat from one period to next period, and hence the integral of the inductor voltage must be 0 over a 1 period. So that is BC1 plus B in minus B O equal to delta T to 1 minus dt, that is VO minus V in into 1 minus D into T equal to 0. So and voltage across L1 is V in into dt plus V in minus Vt into 1 minus D into equal to 0. So from which we get Vc1 equal to V in upon 1 minus D, and from these two relation we get V upon V in equal to 1 upon 1 minus D, D upon 1 minus D. So the change in the input inductor current is calculated from VL1 equal to V in LDI1 upon dt and delta IL upon dt V in upon L1. The value of input inductor current can be calculated from this L1 equal to V1 d upon F to IL1. So the charge of series capacitor increases during the off period by IL2 equal, that is I0, and decreases during the on period by IL1. The change in the charge on C1 must be 0. So dt IL2 equal to 1 minus d IL1, or IL1 equal to d upon 1 minus d IL2, that is d into IN, and the free charge change in input inductor current from these is delta IL1 upon IL dV in divided by L1 IN F. The average voltage across series capacitor is equal to the, so VC1 equal to VO Vin upon 1 minus d, and the rate change of current in the output can be calculated dIL2 upon dt equal to V in plus VC1 minus V upon L2, or IL2 equal to V in dt upon L2. So per unit change in the output inductor current is IL2, delta IL2 upon IL2 equal to delta V in dt upon L2 IO equal to D1 minus dR upon L2 F, and the value of output inductor can be calculated L2 equal to V in dt upon IL2. Similar ripple in the series capacitor voltage can be calculated delta VC equal to delta Q upon C1 1 minus d T IL1 C1 divided equal to 1 minus d dt I in C1. And per unit value of this capacitor voltage delta VC upon VC, that is delta VC1 of V0, or delta VC1 1 minus d upon Vin, that is equal to 1 minus d square T IN upon C1. So value of capacitor can be calculated C1 equal to 1 minus d dt IN divided by delta VC1 upon F, and the charge on C2 decreases during turn off period by the current IL2 plus IL1 plus I2. So peak ripple voltage is delta VC equal to 1 minus dt IL2 plus I2, that is divided by IC2, that is equal to d IN divided by C1F. The average current in C2 is IC2 1 minus d IL1 plus L2 divided by C d into equal to I0 d. So the per unit capacitor voltage variation delta VC2 upon VC2, that is DIN divided by C2 in F. So value of capacitor can be calculated C2 equal to DIN divided by delta VC2F, and the volt ripple in the output capacitor can be delta V0 equal to delta Q0 by C0 delta IL2 T upon 8 C0, and that is TD TV in 8 L2 C0, or DT square V in divided by 8 L2 C0. The per unit value voltage will delta V0 by V0 d minus 1 minus d divided by 8 F square C0 L2, and the value of out capacitor can be calculated as C0 dt square V in divided by delta V0 8 L2. So similarly other two converters can be analyzed and they can be designed for a given specification, and these are the typical waveform of LEO converter with the different elements and input output voltage. So now coming to canonical switching converter, as we discussed, so this is also a buck boost converter. V equal to the input output relation ideal condition is output voltage dVd divided by 1 minus d. So canonical switching converter is a buck boost converter and uses one solid state switch. It has two capacitors, one inductor and one diode, and you can see the three modes. The when switch is on, when diode is on, and one out of the two is on. And the waveform corresponding wave. So coming to the analysis under steady state condition, the voltage across inductor repeats from one time to next period. Hence the integral of inductor voltage must be 0 one period. So V in dt plus 1 minus d t is 0 equal to 0, or V upon V in equal to d upon 1 minus d. Thus it behaves as a buck boost converter. The rate change of the current in the inductor can be obtained during period dIL upon dt equal to V in upon L, or the change typically can be delta IL equal to V in dt upon L, and the value of inductor can be obtained from this for given. So L equal to V in dt upon delta IL, or V in d upon F delta IL. So similarly during off period the series capacitor is charged with the input current resulting in the voltage ripple across it. So delta VC equal to delta Q upon C, or IN 1 minus dt upon C. The value of pressure for given voltage ripple can be calculated as C equal to IN 1 minus dt upon delta VC, or IN 1 minus d divided by F into delta VC. And per unit voltage ripple across the capacitor is delta VC upon VC, that is delta VC upon by 2 in bracket absolute V plus absolute V out. The per unit inductor current can be delta IL upon IL, that is delta IL by 2 in bracket absolute value of IN plus the absolute value of I2. And these are the typical waveform of canonical switching converter in CCN. And this is the waveform during canonical switching converter in DCN. Now coming to the solved problem. Problem number 1, in a DC-DC buck half bridge converter, the duty ratio is adjusted to regulate the output voltage of 24 volt at 5 ampere. The input DC voltage 56 volt. The converter is switched at 40 kilohertz. The considered output filter with the input with the inductor current ripple 20% and its average value of the output voltage ripple 2% and its average value. Calculate duty cycle, value of inductor and value of capacitor. So here the relation in this, you can say half your buck converter is V equal to half 2D minus 1 into Vin, and from which we can find out the D comes actually 0.93 and delta IL equal to Vin by 2 minus V upon 2 DLF. So we get from this L equal to 93 microhenry, and for capacitor delta VC Vin upon by 2 minus VO into D by CL F square. So C from putting value it comes 6.51 microfarad for a given frequency. So coming to second problem, in a cup DC-DC buck boost converter, input voltage per volt, the duty cycle is 0.25 and switching frequency is 50 kHz. The filter inductor is L2 is 0.2 millihenry and filter capacitor is 330 microfarad. Energy transfer capacitor is 220 microfarad C1 and the input inductance L and 0.25 millihenry, and the average load current is I equal to 1.5 ampere. Calculate the average output voltage, average input current, peak to peak ripple of inductor current, peak to peak ripple voltage energy of energy transfer capacitor, peak to peak ripple voltage of output filter inductor, peak to peak ripple voltage of capacitor, and peak current of the transistor. So this is a given circuit, and coming to PO equal to D upon Vin minus D, that comes 4 volt, I in average D I0 1 minus D, that comes 0.5, and R equal to load equal to VO IO, that is 2.67, and delta IL1 VO 1 minus D L1F equal to 0.24, and IL2 is your V0 1 minus D upon L2F S, that is 0.3. So delta VC1 V0 D upon RCF, that is 34.05 millivolt, and delta VC2 V0 1 minus D 8C2 L2 F square, that is 2.27 millivolt, and transistor peak current equal to peak current, so I peak equal to I in average plus delta I2, and that is I peak is 0.62 ampere. Coming to numerical problem third, in a non-isolated DC-DC converter, the DC supply voltage 300 volt DC and required output voltage 120 volt at 10 ampere. The operating frequency 50 kHz. If the peak to peak current variation is L1 and L2 is 20% of their respective average current, and peak to peak ripple voltage of C1, C2 are 500 millivolt respectively. Calculate the value of duty cycle, value of L1, L2, and value of C1, C2. So here solution is V equal to D V in 1 upon D. V in given 300 volt, V is given output 120 volt at 10 ampere. So D comes 0.2857 for frequency of 50 kHz. So we have IO equal to IL2 upon I1, that is 1 minus D upon D, and typically putting I in, I put delta IL1 typically 0.5 and delta IL2 2 ampere. So we get L1 D Vin upon FCL. So putting value it comes 3.4284 millihenry, and L2 comes VO 1 minus D upon FL2. So it comes 0.585716 millihenry, and C2 is 1 minus D V0 8 L2 delta VF square. So it comes 10 microfarad, and C2 VD upon D FSR VC1, that comes 114.28 microfarad. Coming to problem number 4, a DC-DC step boost converter has an input DC voltage and current like 220 volt 20 ampere. The duty cycle is 60%. The input LC filter inductor has very high inductance and its resistance is 1 ohm. The output of the has an ideal L converter. Calculate the value of output voltage, the value of output current, and the value of peak and RMS current of the solid state switch and diode. So V in 230 volt, I in 20 ampere, D is 0.6, R in 1 ohm. Output voltage is your V minus I in R in 1 upon D, that putting a value it comes 500 volt. Output current is I equal to 1 minus D I in, that it comes to 8 ampere. And solid state switch current is I in equal to 20 ampere. So it will state RMS current is under root D I in, that comes 15.49. Diode peak current 20 ampere, diode RMS current under root D 1 minus D I in, that's a 12.649. Coming to problem 5, calculate the value of inductance, output capacitor, peak current of MOSFET, and the supply RMS current of single phase perfect non-isolated buck boost converter in boundary condition between DCM and CCM, and the operating 20 kHz with following thing: B in 220 tier single phase AC supply, DC VO 220 volt, PO equal to 750 with output variable 5%. So given data 220 volt, 50 hertz, single phase supply, switching frequency 20 kHz, PO equal to 240 volt, PO equal to 750 watt. So IA average is PO upon VA, that is come 3.15, 125 ampere. With delta V 5% of VO, that is 12 volt, and delta IL1 5% IN, that is 0.15652. So rectified output voltage out 0.9 VRS, that's around 198, using VO equal to D upon VN. RMS current will be your 750 by 223.4. So V is 198, FH is 20 kilohertz, VO equal to D N upon 1 minus D. So D comes 0.54 and R equal to V square upon P. That comes 76.8, and delta IL is 0.1562. L equal to V in D upon delta IL FS, that's 30.22 millihenry, and C equal to VO D on delta V FI, that is 7.03 milli microfarad, and L minimum RT into 1 minus D square by 2, that is 0.406 millihenry. Now coming to the solved problem 6, find the duty ratio of operation single phase perfectly correct isolated non-isolated buck boost converter in DCM. Discontinuous mode operation, also known voltage follower approach, operating at 20 kHz with following specification: V in 162 to 70 RMS, nominal value 20 volt, single phase AC supply, DC output is VDC equal to 140 to 50 with a nominal value 250, PO equal to 500 watt with output voltage less than 2. The output voltage VDC of buck boost converter is given now V DC equal to D upon 1 minus D. The converter input voltage average voltage to Vn equal to under root 2 Vs upon 5, that is 198 volt. Therefore, the value of duty cycle is 2. Putting this to 0.558. Now coming to problem number 7, the buck boost converter here has a input voltage of 12 volt. The duty cycle is K equal to 0.25 and the switching frequency 25 kHz. The inductance 1550 microhenry. The filter capacity 220 microfarad. The average load current I equal to 0.25 ampere. Determine the value of average voltage VA and peak to peak out voltage. So it is given the circuit here. So we can find out the all data. So V equal to minus 12 and putting value minus 4 volt, and delta VC I upon K. So delta VC is your 56.58 millivolt. Coming to numerical problem 8, the input circuit of input voltage of buck converter is given figure Vs equal to 12 volt, duty cycle is 0.5 and the switching frequency 25 kHz. The filter inductance is 150 microhenry and filter capacitor is 220 microfarad. Energy transfer capacitor 200 microfarad and inductor is 180 microhenry. The average load current is I equal to 1.25. Determine the average output voltage and average current. So putting the value, we get the average voltage 0.4 minus 4 volt and your input current comes 0.42. Coming to problem number 9, a buck converter is shown here in figure. The input voltage Vs 110, the average load voltage is 60 volt, the average load current is 20 ampere, chopping frequency 20 kHz, the peak to peak couple voltage 2.5 load voltage, 5% for load current, 10% for filter inductor current, and determine the value of LE and C. So putting all the value here, R equal to V upon IA, so it comes 3 ohm, K, the typically duty cycle comes around 0.544, and I is equal to KIA, that comes 10.91, delta IL1 is 5% of IA, that's 1 ampere, and delta I 2.10%, that's come 2 ampere, and L equal to V, VA minus Vs minus VF delta I into Fs, that comes 81.82 microhenry, and C equal to delta I upon delta Vc upon delta F, it comes 8.33 microfarad. So coming to problem number 10, a boost regulator in figure has input voltage of 5 volt, average output voltage 15 volt, and the average load 0.5 ampere, the switching frequency 25 kHz, L equal to 150 microhenry, C equal to 20 micro. Determine the value of duty cycle and ripple factor in boost converter. So V equal to VST 22, so it comes typically a duty cycle of 66.67, delta equal to Vs upon V minus Vs upon LV, so delta I becomes here 0.89 ampere. So these are the some of the unsolved problem with the answer. You can solve in the similar manner, and these are the references which are followed for typically developing lecture. And thank you.